Hello AP Chemistry and welcome to 16.9 Salt Solutions. So now we get to take everything we've learned about acids, bases, Ka and Kb, and use it to analyze what happens when a salt is added to water, right? And when we say salt, what do we really mean? Right, we really mean an ionic compound, right? And at the essence, right, when an ionic compound is added to water, what does it do? Right, many of them will dissolve, and once it dissolves, they will then dissociate, right? So then we have this series of things that happens, which means that anytime we put an ionic compound in water, right, we end up with ions. And if we think about everything we've talked about to date, ions are really, right, the conjugates of either an acid or a base, right? And so we need to assess what we're looking at and what to do with it. And while on the surface, this section in chapter 16 seems really slim and there's not a whole lot in here, but I assure you it is super duper important because this becomes the crux of buffer systems when we get there in chapter 17. All right, so make sure this makes sense because it does tie in again later. All right, so salts added to water. Don't forget that even salts that aren't terribly soluble, right, the parts that do dissolve, because going back to the whole concept of KSP, right, even insoluble salts dissolve to some extent, which means that the part that does dissolve will then dissociate, which means it can then interact with the water molecules and subsequently affect pH. All right, so let's think of a few examples to consider, right? So if we had, for example, NaNO3, right, added to water, and we had some FeCl3 added to water, some NH4Cl added to water, and some Kf added to water, right? Then obviously we're going to end up with some sodium ions and some nitrate ions, right? We'll get some iron ions and some chloride ions. Here we would get some ammonium and chloride, and here we would get our potassium and our fluoride, okay? So now we should be clear what ions are present when we add a salt to water. Now, let's analyze our anions, right? So we have some nitrate, chloride, and fluoride. So we have nitrate, chloride, and fluoride as our anions to analyze, right? So what we're going to do, anions, right, are the what? Right. These are the conjugate bases of an acid, right? That's what these are. They are basically the deprotonated form of something, right? So in order to assess its relative basicity, let's go ahead and see what acid they came from, right? So if I were to add an H here, right, this becomes HNO3, which is a strong acid, which means negligible basicity, yes? Because again, thinking about what strong acid means, right? If nitric acid is a strong acid, it dissociates completely. Ginormous K value, yes? Ginormous, which means that the reverse reaction, nitrate plus water, negligible K value, yes? Which means negligible basicity, all right? Just to be crystal clear here, right? HNO3 plus H2O, right? 100% this, yes? Which means that NO3 plus H2O to form HNO3 plus OH minus, none. Does that make sense? Yes, right? Because if this has a ginormous K, this has a K approaching 0. Yes? All right. Moving on to the chloride ion. So if we add an H here, right, it comes from hydrochloric acid. Hydrochloric acid, also a strong acid based on the same exact discussion, negligible basicity. All right. Fluoride, if we protonated it, would be HF. And then, oh, ding, 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 right, this is our weak acid, right? Which means that it does have a relatively small Ka value, which means it has a significant, not large, right, but it has a Kb value, which means it is not a negligible base, which means that we need to consider the concentration of F- in solution if we're going to consider what the pH of my solution is. And obviously, what this means is without some other mitigating factors, the overall solution is going to be basic. Yes, does that make sense? All right. Moving along, how to analyze the cation, right? So our anions are conjugate bases of some acid, which means that our cations are going to be conjugate acids of a base, right? That's what we're going to think of them as, conjugate acids of a base. So let's go back. What are we considering? We have sodium, iron, ammonium, and potassium. Sodium, nope, that's not the right order. That's all right. And ammonium. All right, so same principle, right? If these are the conjugate acids of a base, right, we just need to think about what base did they come from, right? And that gets a little bit more complicated, right? So this one is relatively simple because all we're going to do is envision what happens if we were to add an H, right? Here is the conjugate acid of a base, right? It's not as clear cut, right? Because we can't just like add a hydroxide because it doesn't just work that way, right? But some of them are, right? So for example, these group ones, all right, group ones, we've memorized already, right? We already know that those are strong bases, right? Our group 1 hydroxides and the bottom half of our group 2 hydroxides, right? Which means that these are the conjugate acids of a strong base. So conjugate acid of a strong base, which for the same reason we talked about before, if it's the conjugate acid of a strong base, it has negligible acidity. Yes, does that make sense? Negligible acidity. No tendency to react with water in such a way that it will form hydronium ions in solution. Yes? All right. And then that leaves us with these other two, right? This one is relatively simple, right? We should recognize that as being, right, the protonated form of ammonia, right? Like that comes from ammonia, right? Which is a weak base, which means that this is weakly acidic, which means that a solution that contains ammonium cations, we can expect it to be acidic unless there are mitigating factors. Yes? Makes sense? All right, and here, right, this is that special consideration, which we talk a little bit more in the next slide, in that this is a small, highly charged cation, right? Small, highly charged cations are acidic, and we'll talk more about why in a little bit. All right, so analyzing what's present, right? Super important. So then if we go back here, right, so this had negligible basicity, negligible acidity, that's backwards, but which means that this solution would be neutral, right? This is acidic, this is irrelevant, right? So that means this solution is going to be acidic, right? This was irrelevant, right? This, though, is acidic, which means my overall solution is going to be acidic, right? Here, I did not. This one's negligible. This one is basic, which means the solution of this should be basic in terms of pH, which then by extension, if we had something like NH4 fluoride, right, we have something that is acidic, we have something that is basic, which means that we would have to consider what their respective K values are, right? As in, we would have to look at the Ka of that and the Kb of this, and whichever is greater, that's what it will be more of. Yes, does that make sense? That's what the pH of the solution will more reflect. All right, thank you for listening to this introduction to salt solutions. No worries, there is a part 2 of 16.9 coming. Thank you for listening, be good, and I'll see you soon.